So whenever time you start, my phone was kind of froze up.
All right, welcome everyone. So today we are continuing to talk about confidence intervals when sigma is unknown. So last time, we had shown that if the y sub i's are from a normal distribution and sigma is unknown, then y bar minus mu over s over the square root of n is a pivotal quantity for finding a confidence interval for the mean mu. And we had said that this works not just when the y sub i's are normally distributed, but when y bar is at least approximately normal. So that means we can either have the y sub i's be approximately normal, or we can have a large sample size, such as at least 30. All right, so let's give this a try using this y bar minus mu over s over the square root of n as a pivotal quantity for mu. So on the back side of your choosing a sample size problems, there are two problems on finding confidence intervals when sigma is unknown. And for folks online, this is the choosing a sample size and unknown sigma activity. And looking at problems 3 and 4. So go ahead and try problem 3. Oops, come on. Finding a formula for a 95% confidence interval for mu using y bar minus mu over s over the square root of n as a pivotal quantity. Give that a try and let me know when you have questions.
I did this and I forgot it.
Oh, I don't have this. So we already get to this. So our general strategy for using a pivotal quantity to find a confidence interval is to set up a statement of the probability that our pivotal quantity is between two values, call them A and B. That probability is equal to whatever level of confidence we want. So in this case, we want 95% confidence, so the probability equals 0.95. Then, to find A and B, we use the distribution that we know our pivotal quantity has. So what distribution does our pivotal quantity have in this case? Kyle.
T distribution.
It has a T distribution with how many degrees of freedom? 7, n-1. So y bar minus mu over s over the square root of n has a T distribution with degrees of freedom equal to n-1, which in this case means 7. So then we can find the thresholds A and B so that we have a 0.95 probability of being in the middle between A and B on a T distribution. So the way to do that is by finding those quantiles. If we want 95% in the middle, that means we want a total of 5% in the tails. So we want 2.5% in each tail. So 0.025. So we can do that in R using the function QT. So Q for quantile. So QT of 0.975 will get us B, because that's 0.95 plus 0.025. And QT of 0.025 will get us A. Or if your calculator has an inverse T function, you can do it on there as well. All right, so that gets us A is negative 2.36, ... and B is positive 2.36. What's our next step?
Solve for mu.
Solve for mu. We want to get mu by itself in the middle of this inequality because mu is the thing we're trying to find the confidence interval for. So we can multiply everything by s over the square root of n. And subtract y bar from everything. That'll leave us with negative mu in the middle. And then we can multiply everything by -1 to get just mu in the middle. And that has the effect of reversing the directions of the inequalities. So we have y bar plus 2.36 s over the square root of n, and y bar minus 2.36 times s over the square root of n. Questions about this? All right. So this is a specific case where n was equal to 8. But in general, I don't know what that was. There we go. Our general form of the confidence interval for mu when sigma is unknown looks like this. So y bar plus or minus a multiplier that's coming from the t distribution, which we can write as t sub alpha over 2 comma n minus 1, because we're specifying the degrees of freedom, times s over the square root of n. And to get this on your calculator, you can press the stat button and then go to tests and t interval. And it will give you options to, do you want to input the data, in which case you'd put the data into your list L1, which would be available under stat edit, or input the stats, in which case you'll put in the sample mean and the sample standard deviation and the sample size, and it will compute the confidence interval for you. Why don't you go ahead and try using your calculator to solve problem 4. Yes, and Isaac, maybe when you're done, you can lend your calculator to Sam. So when I did this, I got 10.77 to 15.63. Does that agree with what other people got? Cool. So what is this saying? Can someone interpret this confidence interval for us? Nine?
I feel like if you did this experiment and it put in a amount of times, that 95% of the time, the population would be in the
The population mean we're thinking of as just being some value.
sample.
Not quite. Can someone refine Niall's suggestion? Kyle?
To the mean for the track level, you calculate it,
What about it?
what would be in the confidence interval, would have 95%.
except we don't want to use chance because the mean trap level is some value, it's not a random variable.
We have a 95% confidence of it being within the interval.
Yeah, we're 95% confident that the mean trap level of all young women from this population is in this interval. You can also think of this in terms of repeated sampling, which was kind of what Niall was getting at, which is in repeated sampling, about 95% of the confidence intervals that we would get would contain the true mean trap level in the population. But there's nothing special about this confidence interval that we got that would say those other confidence intervals would or wouldn't relate to this in any way. Just this is one particular confidence interval that we got from one sample. And we know if we did that repeatedly, taking multiple samples of the same size, about 95% of the intervals we computed would contain the true value. Questions about this? All right. So a note about terminology. What do we call this interval? So for large sample sizes, so large degrees of freedom, the quantile value, the alpha over 2 quantile value from a t-distribution is going to be very close to the alpha over 2 quantile value from a normal distribution. Because you've seen this in lab, you've compared the normal distribution, standard normal distribution, with a t-distribution with different degrees of freedom. And you saw that as the degrees of freedom increases, the t-distribution got closer and closer to a standard normal distribution. So when people only used paper tables to get them the cutoff threshold values, they called this y bar plus or minus the t cutoff times s over the square root of n. They called this the small sample confidence interval, with the idea being that once your sample size is large enough, then it's not really worth figuring out what the threshold value should be from a t-distribution. We'll just use our normal probability table and get z sub alpha over 2 instead. But now it's easy to compute the t sub alpha over 2 quantile value using a calculator or using a computer. So I tend to think of this as being the sigma unknown confidence interval, and to use this for any sample size if you don't know the population standard deviation. All right, so let's move on to a related question, estimating the difference of means between two populations. So if we knew sigma sub 1 and sigma sub 2, so the standard deviations of those populations, 1 and 2, Then we could use our principle from that table of common point estimators that said our confidence interval can be our point estimate plus or minus a standard normal multiplier times the standard error. So that's going to give us, that should be y bar, not y. Fix that. So our point estimator is going to be the difference of sample means from our common point estimators table, plus or minus z sub alpha over 2. And then we said that the standard error for y bar 1 minus y bar 2 was the square root of sigma 1 squared over the sample size from group 1 plus sigma 2 squared over the sample size from group 2. If the sigmas are not known, then we simply replace this with using the sample standard deviations S in place of sigmas and using a t distribution multiplier instead of a normal distribution multiplier. And here I've just left the degrees of freedom. Here I've just written it as df. The degrees of freedom for this calculation are complicated. If you need to solve a problem like this by hand, you can approximate the degrees of freedom using the minimum of the sample sizes minus 1. So take whichever group has the smaller sample size and subtract 1 from that. But more commonly, when you're finding these confidence intervals, you'll have either R or a calculator with you. So to do this on a calculator, you can go to stat tests 2samp t int. So let's give this a try. Try problem 1 on this confidence intervals for variance and a difference in means. So for folks online, oops. This is this confidence interval for a difference in means problem. All right, can someone tell me what they got for the confidence interval? Kyle, what'd you get?
63 and 113.
63 and 113? Does that agree with what other people got? Sam, what'd you get?
I did it my calculator, and I got negative 111.9 to negative 64.1.
All right, any other nominations?
I just typed it wrong, so I figured 0.12, 0.4, negative 2.55.
Like that? All right, so it looks like we have at least two differences going on here. So Kyle, it looks like you did literature minus engineering. So your confidence interval ended up being positive. And Sam and Isaac, it looks like you did engineering minus literature. So yours ended up being negative. Besides that, these numbers are pretty close. 63 and 113 is what I came up with when I was using, sort of doing this by hand and using the approximation for the degrees of freedom. So Sam, were you using the 2 sample T interval?
Yeah.
Okay. And Isaac, were you also using the 2 sample T interval? Okay, so those two methods should give you the same results because you were doing the same thing. So I think one of you probably had a small typo in.
Oh, I think I accidentally put C instead of T.
Ah, that'd do it. All right. So we'll get rid of that one. And go with this. All right. So can someone tell us what they said for the interpretation of this confidence interval? Sam?
I took a guess, it's like we are 99% confident that like 63 to 13 more meters.
That's a good thought. But the thing that we're investigating here isn't the number of engineering and literature majors, it's the mean verbal SAT score among engineering and literature majors. So someone else want to sort of take a stab at finishing this sentence? Isaac, what would you say?
We're 99% confident that the difference between the mean verbal SAT scores and literature. That range.
Did anybody else phrase it differently? Kyle, what'd you say?
Phrase it by saying, there's a, oh wait, they use this chance, never mind.
Yeah, so we do want to stick with the idea of being confident. Another way we could phrase this would be to phrase it as sort of a more direct comparison rather than in terms of the difference of mean. So we could say we're 99% confident that the mean verbal SAT score of all literature majors is between 63 3.55 and 112.4 points higher than the mean verbal SAT score of all engineering majors. Isaac.
Would it be wrong to say difference because that technically could be like difference lower?
It's not wrong, but I think this second way makes it a little more clear which way the subtraction is going. All right. So take a moment to read problem 1B and think about the answer to yourself. All right. So let's imagine that we could measure all engineering majors and get the mean verbal SAT score, and measure all literature majors and get the mean SAT score, verbal SAT score. And we want to know, are those two means different? Or is it believable that they could be the same? Let's see thumbs up if you think there's evidence that they're different. Or thumbs down if you think, no, it's believable that they could be the same. Yeah, I would say thumbs up here. What about the confidence interval is telling us that there's evidence that those two means are different? Maria?
Zero is not in it.
Exactly. So yes, because 0 is not in the confidence interval. So our confidence interval told us that we're 95% confident that this difference in means is between 63 and 113. That means we're at least 95% confident that the difference in means is not 0, because 0 is not between 63 and 113. This is assuming that the samples were representative. Any questions about this problem? All right. So we've just talked about confidence intervals for means and a difference of means when sigma is unknown. There are some circumstances when you might want a confidence interval for sigma itself. This comes up in like quality control, for example, when you want to make sure that your precision of a particular machining process is within a certain range. So take a look at problem 2 and think for a moment to yourself about what you might use as a pivotal quantity. All right, so what characteristics do we need a pivotal quantity to have? Kyle, tell me one thing.
It would be a function of the pressure versus y sub I, and I guess in this case, standard deviation.
Yeah, y sub i's and sigma or sigma squared. And no other unknown quantities. And here we have that the mean is unknown. So that means that we also need it to not be a function of mu. Cool. What other thing do we need our pivotal quantity to have? Sam?
The distribution can't depend on sigma.
Cool. All right. So function of the y sub i's. So just to remind you, some options here that we have are it could depend on n, it could depend on y bar. It could depend on s, the sample standard deviation, because that's a function of the y sub i's. There are other options, but I would say that these are sort of our most common functions of the y sub i's that we end up seeing in pivotal quantities. All right, so think back to our distributions based on the normal distribution. For something that might be a function of one of these and sigma, but not mu, where we know what its distribution would be. So if you're looking back in your notes from chapter 7, that's a good idea. Talk this over with people sitting near you.
Stay home.
So as a hint, you are looking for something that involves n and s squared, but not y bar in this case. Any nominations? Kyle? Something with a chi-squared distribution? That sounds good. What are we going to use that's going to have a chi-squared distribution? Niall? Yeah, n minus 1 times s squared over sigma squared. That's going to have a chi-squared distribution with n minus 1 degrees of freedom. Sam, question? Good question. The statistic here, the n minus 1 times s squared over sigma squared, that depends on sigma, which is good. We want that to be a function of sigma. But the distribution that it has is chi-squared, and its degrees of freedom just depend on n, not on sigma. So the distribution that it has does not depend on sigma. All right, we are about out of time, so I'm going to put my key for how to find the confidence interval using this pivotal quantity up on Canvas. And I will see you on Monday for the start of hypothesis testing. Have a great weekend.